Okay, now I want to. One more time. Bro, if it's on the test, what was it?
I hope this probably.
I'm not editing that. No editing.
No cuts.
No cuts. One take. You guys ever see Birdman? Birdman? No cut.
No cut.
Is it 1917?
1914, I thought.
1914?
That's a bullshit. I'm kidding.
I'll never listen to you again. What's the name of the World War I movie where that's like one take? It's like one take?
1917.
Yeah, that's what I thought. That's what we're doing today.
I'm going to war.
One cut. Alright, it's fine.
Real. I'm gonna do this right.
That's why you get 2 burgers.
Space out. You have to stop at some point. Still.
Exactly.
Be sure to ruin all of I know, that's what I see it. I know.
That's actually
If it doesn't say there's anything, this is like your initial condition. I know.
It's a better way.
I mean, the point of more circle is that as you rotate, we don't get it. Okay, 501. Let's do it. So I'm currently recording myself. This is something I want to do for a while. Is record these and kind of see if I can like put it on YouTube or something, because I'm graduating. And I think that, you know, maybe in the future people can look back on these and learn a thing or two. So don't say anything I wouldn't. I'll set the tone for you guys. But yeah, let's get started. So midterm number 3, what are we worried about? Whatever that is. Combined loading. No 3D Moore circle on this test. I'm not going to show you how to do it because it's going to be a waste of our time. And also, I'm not 100% sure how to do it. Unless you said anything about it. Yeah.
Shear stress due to torque.
Okay.
Deflection.
You're probably only going to have to do a 2D Moore circle, just to reiterate. Yeah, so I mean, what? With the table, yeah. That's what you're going to have to do in the exam. So, right, so.
Can we also do some without the table with the direct integration? Because he said it's between that and the table.
Could do that, but it's like almost certainly. I feel like it's not going to be on the end. I've never seen it again. If we have time at the end, I think. But it's very time consuming. There's the one problem that's like, oh, what are the constants? What are your boundary conditions going to be? So we could like talk about that a little bit. Yeah, so I mean, I guess this midterm is really, I think it's really interesting because it's like, what was this class all about? What is the point of this class? I don't know. What the hell? What are we doing? Does anyone know what the whole class is about? Yeah. It's like, is my material going to fail? So I have a loading condition. Is my material going to fail? And then also, is my material going to deflect? How much is it going to deflect? That's the whole point of the class. That's exactly what this is. You have some weird shape thing, and then you have some loads that are going to be on it, and then you're like, okay, what is the stress going to be? Is this thing going to fail? So that's the whole point of this class. You mechs are going to get into machine design, and that's a lot more about like failure theory, and you get more into like, is this going to fail? This is more like what is the stress, and then you could theoretically compare that to your failure stress somehow. But yeah, I am going to start off with like my own invention. I realize this is my own invention because I realized that Dr. Hazelton never said anything about it, and people are like, oh, this is really helpful, thank you. And so yeah, I call this the, what is it called? The stress tree. Okay, this is the stress tree. So we talk a lot about what is like stress, right? And nobody knows what stress is. And so we have two types of stress. What are our two types of stress?
Shear.
Shear. I'm going to put normal over here. What is the symbol for normal? Sigma. And then shear. What is the symbol for shear?
Tau.
Tau. Perfect. And so within those two regimes, what sorts of things cause each of them? What sorts of things cause normal stress? Sorry?
An applied load.
An applied load. Can we be more specific? These are all applied loads.
Axial load.
An axial load. So if we have an axial, I'm going to say an axial force. How do we determine the axial stress caused by an axial force? P over A, thank you. And so this would be like a P. What is another thing that causes normal stress?
Bending.
Bending. So if we have bending, what causes bending?
Moment.
A moment. So a moment causes bending, moment we call M. And then the stress due to bending, how do we calculate that?
My over I.
My over I, or MC over I. We'll talk more about that because that's the hardest one, I would say. How about shear? What causes shear stress? Somebody said it earlier. A torque causes shear stress. Torques we usually call like a T. How do you calculate shear stress due to a torque? TC over J. So shear, I'm going to call it torsion, is equal to TC over J. And then there's another thing that causes shear stress.
Shear force.
A shear force. Thank you. That would be like V. And so this tau would have a tau sub shear, and then what's the equation?
dq over it.
dq over it. Thank you. Okay, and so if you don't feel totally comfortable using all these equations, that's okay, because we're going to get to all of them. Yeah. Bending does not cause a shear. Moments would cause bending, and that's only normal. Okay, right, this is just a good thing to have in your equation sheet, and it's also good to remember, because like, in previous exams, there's been things where it's like, what is the normal stress at this point? What's the axial stress at that point? And this is exactly like telling you what all those things are. Axial just means this. Normal is like the combination of these. Yeah. I think I'm going to start over there, and then we'll kind of make our way back over here, and I can erase this later. I think I'm just going to leave this up here for now. So, okay, this is a good problem right here. I have one issue with it, and that is that this distance, you see this B1 is 80, and then this B3 is 40. What is 80 plus 40? Any 120? We got some smart kids here. Do you see how B2 is also 120? Pisses me off. We're going to change B2 to be 160. Okay? Hopefully we all remember that, because I don't really want to redraw this, and I don't think I can do a much better job than this picture right here. So we're just going to start on this. So this problem, this is going to basically almost, yeah.
Which midterm is this?
This is, I think it's spring 22. Spring 22. This is a good one to start on. This is basically going to be your first problem in the exam, if I had to guess. But we'll go over everything to make sure you're ready for whatever, but I'm 90% sure this is going to be your first problem. Not this geometry, but this problem type. And so this problem is asking, for the loading shown, compute all of the internal actions. What did I just talk about? What are those things over there that I wrote? A little bit small?
Internal.
Those are all internal actions. The axial, the bending, the torque, and the shear force. Those are all of our internal actions. P, M, T, V. So we want to compute all the internal actions at the cross section that cuts through point B. show all these clearly on a large diagram and label them accordingly. Next page, whatever. Okay, so starting off, we know what our internal actions are. They're going to be axial, bending, torque, or shear force. So PMTV. We'll talk about what those mean in a sec, but we're going to look through them at the cross section that cuts through point B. So I'm going to start off by drawing that cross section. I'm going to draw it in the top left over here, and this is going to be it right here. It's perfect. Where is B at? I don't think that matters too much, but I'm going to put B right here. And then this is very key. Which way are my axes going? What axes are in this plane? Y and Z. Which way is Y going? Up, thank you. What about Z? Left, thank you. So the biggest thing with this first problem is understanding like 3D, like Cartesian space. So a lot of this is intuition that if you don't have right now, you're gonna have to kind of grind it out. Because there's no other way to get better at it than just to like do this with your hand a bunch. So, right, okay. The way I like to tackle this is to split each of the forces that are being applied up and tackle them one at a time. So we're going to start off with, I guess, the 3 kilonewtons. And we'll start there. So we have the 3 kilonewtons. And we're remembering that this is, B2 is 160, not 120. I wish I could write it somehow. Maybe I could do like, I don't want anyone getting confused. So I'm just going to do this really quickly. Oh no, not 160 font. No.
You can just let that entire slide go up and then just draw on the board.
Yeah, but then I don't want to. Yeah, you're right. I should probably do that.
He's already done.
I'm already done. This is fine. I don't know why. Okay, this is good enough. Okay, so we're looking at the 3 kilonewton load. And the thought process, I'm going to teach you kind of my step-by-step. There's the intuition of knowing what way an action is going, like a torque or a moment, is one thing that is nice to build, but I'm going to try to teach you the most like step-by-step, like you don't need the intuition. You need as little intuition as possible in order to still get the right answer. But there's still a little bit of right-hand rule that you have to do. So starting off with the 3 kilonewtons, you have to think about it as if the goal is to get your force to the centroid of the cross-section. We know that the cross-section that we're interested in is this one right here that cuts through point B. Is the centroid of the cross-section, is the 3 kilonewtons going through the centroid of that cross-section? Yes or no? No, it is not. How will we get it there? Moving up. Which way is up? Can we be more specific? The Y. So when we move it up in the Y, what plane do we move it up to? The XZ. And so between X and Z, this is going to seem weird, but bear with me. Between the two axes, X and Z, which one is our 3 kilonewtons perpendicular to? The Z. This means that we're going to have a moment about the Z axis. And this might seem like kind of like out of left field, but this is just how it works. And I think it's a good way to go about it. So we have the 3 kilonewtons right here. We want to move it to the centroid, right? And remember that our vector has an infinite line of action going this way, or it just has an infinite line of action. And so when we move it up right here, it's going to be going through the centroid. That's what we want. And when we move up there, we're moving it to a certain plane. Because before, the XY plane, the 3 kilonewtons is already going through it. Can we all see that the 3 kilonewtons is in the XY plane? Yeah. And also, it's piercing the YZ, because the YZ is like a flat wall over here. The 3 kilonewtons is an infinite line of action, so it ends up piercing through. So it's touching those 2 planes already. We want it to be touching all 3, because if it's touching all 3, since our coordinate system is centered at our point of the center of our cross section, we want them to be touching. We want our 3 kilonewtons to be touching all 3, because that's the point we're trying to get it to, right? And so, in order to get it there, we have to move it up to the XZ, because that's the only plane it's not touching at the very beginning. And so when we move it there, there's this little trick that I'm teaching right now to tell you where the moment is. And that is, we moved it to the xz, we say between x and z, what are we perpendicular to? The 3 kilonewtons is perpendicular to the z, as we just said. And so that means that we have a moment about the z-axis. Okay? I'm going to say that probably like 2 more times before we're done here. But that is how it works. Now from here, we have to say, is that 3 kilonewtons causing a positive moment about the z or a negative moment about the z? And this is where you're correct, but slow your roll. Yeah.
Wouldn't the, I'm just trying to conclude, wouldn't the 3 kilonewtons also be perpendicular to the y?
That's true, but the fact that we moved it up to the xz plane, this is just a part of the trick that I'm teaching. The y is eliminated because it's not a part of that plane that we moved it up to. So that's why you have to ask yourself, what plane am I moving it to? Because, oh wait, if these vectors are Cartesian and they can always be decomposed, there could be some diagonal vector, but you can always decompose it into its x and y and z, right? It's by nature, it's going to be parallel to one and perpendicular to 2 others. And so the plane that you move it to, it's going to be parallel to one and perpendicular to the other. Because the one that it's already parallel, or already, I don't know what I'm trying to say, but that's just how it works.
Yeah, it's because it's like constantly on the y-axis, but you're moving it up to the z.
Yeah, you're moving it to the xz plane.
It is.
And then out of those two, you ask x or z, which one am I perpendicular to? We're not including y because that's not in the plane that we moved to. Okay. Right, so now that we know where our moment is, or sorry, what way it's going, it's in the z direction. We have to ask, is it going positive z or negative z? And so this is the part that requires a bit more intuition. So what I like to do is I put my hand at the cross section, and then I think, okay, it's either going this way, this is negative z, because this is positive z right here. Either going that way or that way, right? And so you can use your fingers. Remember, the fingers are the action, the thumb is the actual arrow. We know the thumb has to be along the z-axis, so we keep it that way. We look, is it like this, is it like negative, or is it like that, like positive?
Negative.
Right. Is that clear, is that not clear to anybody?
So thumb's always on the z.
Thumb is not always on the z. Thumb is just on the z because we determined it's an mz based on the whole plane thing that I was just talking about earlier. And then we find out that it's negative because of our fingers. You can do that. You can just jump straight to the fingers if that's intuitive for you. I'm trying to teach the plane thing because it might not be, there's so many different axes and so many different directions the moment could be in that, there's about 6 actually, about 6 directions. It's nice to narrow it down to just positive z or negative z. But yeah, if you can't see, if your thumb is going this way, it causes the action that 3 kilonewtons is doing. So now, I kind of skipped a step, that sucks. We say there's an mz, and it's equal to negative, because we just determined it's meant negative. I'm going to convert to newtons and meters, so this is going to be 3,000 newtons. And then we multiply by we moved it earlier. How far did we move it? 160. So we're going to multiply that by 0.16 meters. I converted it to meters by dividing by 1,000 because it's in millimeters. Okay, and that's equal to negative 480 newton meter. Okay, any questions on any of that stuff that I just said? I'm going to repeat it like 2 more times. Or maybe even more if we do another one of these. Good. Okay, I kind of skipped this step. When you first start with one of your forces, you need to ask yourself, it's either going to be a P or a V. Which one is the 3 kilonewtons? P or V? P. It is a P. So P, and then we say, what direction is it going in? What direction is the 3 kilonewtons parallel with? X. The X, thank you. And is it going in, excuse me, the negative X or the positive X direction?
Negative.
We say the negative 3 kilonewtons. Okay, now, yes?
I don't know if it's P or V.
We'll get to that. Thank you. The next one we will get to it, yes. We moved our 3 kilonewtons up to here. Is it going through the center right now?
Yeah.
We're done. 3 kilonewtons is over. Okay, now we are on the 5 kilonewtons. So we say the 5 kilonewtons, and I add a colon. And then the first thing is to say, is it a P or a V? And then this is to get to your question. The way we determine whether it's, does anyone know, P or a V?
V.
V. Why do we know it's a V? It was on the test. Great. It's parallel. So the way we delineate between our P's and our V's is by looking at the direction they're going. So the most important arbiter in terms of deciding whether you're a P or a V is looking at your cross-section of interest. So our cross-section of interest is right here. This cross-section, whether our vector, our force, whatever you're gonna call it, is perpendicular or parallel to this cross-section determines whether it's a P or a V. And so, would you guys say that the 3 kilonewtons was perpendicular or parallel to our cross-section?
Perpendicular.
Perpendicular, it's going into it, right? And so, that is gonna make it a P. Going into is like pushing on it, right? Or pulling out, compression or tension. That makes it a P. And so therefore, anything that is parallel to our cross-section is gonna be a V. Okay, and so in this case, we can look at the 5 kilonewtons. We see it's going in the Z direction, and we also see, hopefully enough, we see a Z right here. And so that Z is parallel to our cross-section. This is a VZ. So VZ is equal to, is it positive or negative? Thank you. Okay, now, is it going through the centroid of our cross-section?
No.
How do we get it there?
2 different actions.
Right, we're gonna need to move probably one this way and then one back up. So I guess I'll start off going up. Maybe? Yeah, we'll go up first. Okay, so we're right here. We're gonna move it up. What plane are we moving it up to? XZ. So out of X and Z, what are we perpendicular to?
X.
Okay, so we're gonna have an MX. So now we have to determine which way it's going. Is it going positive X or negative X? So the only way to do it, yes, I think you're right, is to get your hand right here. You know it's either going in the negative X or the positive X. And so looking at what the force is doing, imagine it's like a lever that we're cranking. Like if you move it like this, it's gonna go like, what is that, counterclockwise, or that's clockwise? And so that makes it negative. Okay. And so I did something wrong. What did I do wrong?
Called it a moment.
I did. Okay, how far did we move it?
160.
160. Is that 800?
No.
What is it? Can somebody with a calculator please, for the love of God, help me out?
Is it 800?
You?
Might be. I don't know.
It's like actually astounding to me how nobody ever like.
800.
Wow, thanks. Great going, guys. Okay, why is this not an MX? What else could it possibly be? It's a torque. What makes it a torque? In the exact same way that P and V, the only thing that delineates them is what direction they're going with respect to the cross-section. Your torques and your moments, the only thing that delineates them is the fact that they're going either in or out of the cross-section or parallel to the cross-section. So in this case, we have an X-facing double arrow. Our double arrow is going into the board like so, right? And so that is going into our cross-section. That means that we have a torque. Torque means that it's going perpendicular to cross-section. Moment means it's going parallel. Are there any questions about that? It's the exact same thing. It's just you have to know which one's which. And so some people do like, I saw somebody do like parallel to cross section, or maybe, well, how do you do parallel? Like this? This is perpendicular to cross section. This is parallel to cross section. And then this is perpendicular to cross section. If that helps you remember, more power to you. Okay, so we moved it up to the XZ. Now where do we have to go?
To the left.
To the left. So what plane are we moving it to when we do that? The YZ. This is the YZ right here. Before we're down here, we're not going through the YZ at all. We have to move it leftwards, like you said, aka in the negative X direction, to get into the YZ plane. Out of Y and Z, what are we perpendicular to? Y. And so that means our moment has to be either, we know it's a moment. Why do we know it's a moment? If it's in the Y.
Parallel.
Y is parallel to our cross section. That makes it a moment, not a torque. we know our moment has to either be going up or down, negative y or positive y. Which one does it look more like to be? Just by looking at that 5 conings.
Negative.
Negative, thank you. Hendrix, you're done, okay? No more talking. I'm just kidding. I'm just kidding. Please, you're helping me. But yeah, so this one's a little bit harder to see, right? But I might do those 2D drawings in a second, just to make sure that we understand. But yeah, so we know it's an my, and like Hendrix said, it's a negative. And it's going to be 5,000 newtons by how far did we move it? 120. So that gives us 600 Newton meter. Okay. So now that we moved it there, are we at the center of our cross section?
Yes.
Yes, we're done. Okay, we're not done, but we're done with this part. Now we move on to the step where we draw everything. So this step is a lot easier because it's all you do is just draw all the things that you just wrote down. So starting from the top, we have our px. We know it's in the negative x direction. Which direction is that? Which way is the negative x direction? Negative x direction?
Into the board.
So if you see right here, the x is coming actually out at us. The positive x is. So that means the negative x is going in. And so how do we draw a force going into a board? Circle with an x in it. Perfect. So I draw that and I call it px. We already defined px as being this value. We don't need to write that on there. It's just clutter. Px is good. Now, what's next? Mz. Mz is going in the negative z direction. So I look at this guy. Positive z is going that way. Negative z is going like this. So I draw this. Double arrow and I write mz. Boom. Next one is the vz. That one's going in the positive z direction. So on the other side, to avoid clutter, I'm going to draw this v right here. I'm going to call it vz. Next is tx. I'm going to skip that one real quick. My is going in the negative y direction. So positive y is up there, negative y is this way. Did it turn off? Honk, honk. I label it. And then finally the tx. How does the tx work? It rotates. We can draw it as like a clockwise or counterclockwise thing. So the first thing to say is that it's going in the negative x direction. So we know the positive x is coming out at us, like we said. So negative is going into the board. So I put my thumb into the board, and then I start rotating. You can see it's a clockwise rotation. And so we do a little bit of this, and we can label it tx. And then we are done. Okay? Any questions on this whole step? Yes?
The 120 millimeters on your moment y, was that from where?
That's because we moved it 120 millimeters to get back to the origin. So let me get this back up. All the distances are from when you move it. Like how far do you have to move it to get to that plane? Or to the origin. So when we were moving it 120 millimeters, because remember we moved it to the zy in the step from here to here, and that's 40 plus 80 gives you 120. And that one's the my because it's perpendicular to the y, which is the perpendicular, out of z and y, it's perpendicular to the y, and so that's an my that's being created. Okay. I kind of want to make drawings, like, it always sucks, because I want to ask you, like, is there anyone who doesn't understand this? And then you're like, oh, I don't look like a big dumb idiot who doesn't understand it. But like, the whole right-hand rule thing is really important. Yeah.
I have a question.
Mm-hmm.
So you said, sorry, which ones were perpendicular and parallel? Was axial and torque that were both perpendicular?
Axial and torque are perpendicular, shear moment are parallel. So think of it as the double arrow itself. For the moments, like the double arrow itself, if you point your thumb in that direction, that thumb is parallel to your paper. Yeah.
So whenever you see a problem like this, like your first step is you just take that cross section and you're trying to analyze what all the forces are doing across all of the principal planes.
Exactly.
Essentially.
One force at a time.
One force at a time.
Mhm.
Okay. And then your goal is to get something like that. Okay.
Yes.
So this is taken at like against the wall support, like that's what our cross section is.
Mm-hmm.
Is there a reason that we don't have reactions?
It's because it's the exact same reason, like, so what can we say about all these actions? Maybe midterm 1, I hammered on about it. So the 3 kilonewtons and the 5 kilonewtons, what kind of loads are these? These are like,
External.
they're external, right? What about all the actions that we just came up with? They're internal. So when we do like a cut to find internal or external, do we care, what side do we care about? One or the other is what I'm trying to get at. We only care about one side or the other. And so everything that's not on that other side, or sorry, that is on the other side just sort of vanishes. And all the actions are what we care about. This is exactly what we just did. We just did it in 3D. It's the exact same thing. Okay, and so that leads very nicely into what I was just gonna say. If we imagine that we are looking at like something like, I'm gonna pull my mouse out. We're doing art today. Bear with me. If we imagine for a moment, oh my God, the sense. If we imagine for a moment that we're looking at this cross section instead, and that there's also a force right here, maybe, do you think that we care about that force? We do not care about that force. The only forces that we care about are on the side that we know stuff is going on. Technically, you could calculate all the reactions and do it the same but on the opposite side. But that's a less intuitive, I would say. But yeah, we had this on my exam. There was a force that was on the other side of the cross section. They like said, oh, look at this cross section. And then you put a force over here. Ignore that force. If it's on the other side of the cross section, ignore it. So that's an important thing. I don't know if you ever like said that explicitly for us. I doubt we said it explicitly for you guys. So, yeah, okay. We are already 30 minutes deep. I think it's time to move on. Moving on, good? Okay, cool. I think I'm going to stay over there because having these equations up is going to be very nice. Oh, I should have asked if anyone wanted a picture. You guys are fine. You got a video? Yeah, I got a video. For posterity. Okay, I guess like I don't need to really, yeah. Not always. It depends on like whatever it's defined as, really. And if it's not defined, like you can define it as whatever you want. This is kind of like a right-handed coordinate system. If you've ever heard that before, it means like do this with your hands, and then like X, Y, Z. In this case, like Y is typically always up. Z is coming out here, and you see how like the X is coming out? It's following like the shape of my hand. That's what people mean by a right-handed coordinate system. Yeah?
Just because in the last problem we did, we also had the z-axis positive towards the lens. Is that's like standard?
I think you kind of standard with the right-handed coordinate system. If X is like coming out like that. But like, all of these things, like the labels that we make for everything, the coordinate systems we set up, it's all arbitrary at the end of the day. The only thing that's not arbitrary is making a standard between things, like counterclockwise positive, clockwise negative. That's like a standard because like if we did it another way, then people might get confused. But yeah, that's one thing I like to talk about here is like I was talking about this, right? Positive X is coming out at us. Yeah.
Sorry. The torque in this one is pointing in the opposite direction, but would that torque would still be negative in the other one, even if the z-axis.
Let's use our right-hand rule to check. So I'm trying to prove something a little bit here. You know how like in statics you're like, oh, counterclockwise is positive always, right? You see how with my right-hand coordinate system, which way is X going? Out of the board at us, right? So a positive X, a positive torque would look like this, right? Which way is it going, that positive torque? So that's where the whole counterclockwise positive thing comes from, if you never knew that. But yeah, so with that in mind, is this torque positive or negative? Positive, yeah. We're not going to really care too much about the sign of it here, I guess, but yeah. Any other questions before I get started on this? Yeah.
On the exam, I'm gonna need to mark it properly, like if it's far.
In the previous step that we just did, yeah. So like, yeah, I mean, it needs to be going the right way. Like you can't have it like, if it's clearly going like a clockwise thing, it has to be going in the clockwise direction. I don't know. So yeah. Okay, getting started on this. I'm not gonna redraw this because we already have it up here. This might seem scary, but it's really, really not. You've done all these things before. All these things are things you've done before. Let's go step by step. So, how many actions do you guys see here? 1, 2, 3, 4. Okay. Now let's go easiest to hardest. Which one do you think is the hardest, or sorry, the easiest to do? VZ. I would disagree. I would say VY is the easiest. So yeah, I guess I have to redraw it. Here's B, and then VY is going like so. So how do we calculate? So this step is basically saying, all right, we just did the last step. Now we want to find out what the stress is at a certain point, right? And so the way this works is we're just saying like, okay, we know what all of our actions are. Now let's find the stress at B. So for a shear force, how do we find the stress due to a shear force? dq over it. I gave it to you. So we're going to call it tau shear y. Okay, and that's going to be equal to vq over it. What do all these mean? So the v should be easy, right? That's just about, so this is a symbolic question, so we're going to leave everything in terms of like symbols. The v should be pretty easy. That'd be vy. I would assume he's fine with you keeping it just as I, yeah. Okay, and then q and t are the hard ones. So the way that vq over it works is v and I are pretty easy because that's just the v and the I of the cross section that you're looking at. Q and t get a little weird. Can anyone tell me kind of how that works? Yeah.
For Q, you have to like look at your area above your point or something like that.
You're getting ahead of yourself. How do you get that? What point? How do we get that point that you're talking about?
Like
It is something at B, but it's not just above that.
I think the area times the center.
Making a cut.
You gotta make a cut, yeah.
I was gonna say, another cross section.
You gotta make a cut. So how do we make that cut? The first thing that you do is you kind of analyze the shear flow. This is something that kind of makes more sense for an I-beam, but here it's pretty simple. If you imagine like the Vy is like the flow of water, you can imagine that like little water droplets are like going through like so, right? At point B, what is parallel to that shear flow? What direction is parallel to that shear flow? Perpendicular. The Z. Coordinate system. I was kind of just looking for more horizontal, right? So if you make a horizontal cut at that point, we usually would divide the shape into two shapes. But in this case, did we divide the shape into two shapes? No. So the next step is to say, okay, Q is equal to AY bar. In this step, you say A is equal to the area of the cut that you just made. The area, okay. It's just weird with this problem. Maybe I shouldn't have started with this. But you're supposed to look, if this is the centroid right here, normally the cut would be like not up there, right? Or maybe not normally, but just imagine it's not. You say, okay, I have two different areas. I have this one above the cut and this one below the cut. Is above the cut away from the centroid or towards the centroid? Away. So you're looking for the one that's away the centroid, away from the centroid, which would be this one up here. And so since the area away from the centroid in this case is 0, that means that all of our shear stress due to this is 0 at that point. So that's why we chose Vy first, is because it does nothing. It's kind of, I don't know if I'm explaining it the best, but I'll do the other one right now and we'll see kind of what I mean by that. Okay, so we have tau shear Z. Okay, so we have Vz over I. Okay, now we have symbols. So, this time, I'm going to erase our Vy because we're going to go one at a time here. We have a Vz. Is it going left or right? Going right. Vz, we can imagine our shear flow kind of going like, So now which direction is perpendicular to our shear flow? The y. So if we make a cut at our point of interest in that direction, we split the circle into two parts. In this case, the two parts are equivalent to each other, right? They're like, it's mirrored, right? So step one is saying, what is the thickness of the cut that I just made? The diameter, right? I wish we had numbers kind of, but it's okay. The diameter is how thick the cut, we just cut through a diameter's worth of material here. So our thickness is gonna be D. And now we have to do Q. So Q is AY bar, where A is the area of the one that's away from the centroid. Which one would you say is away from the centroid, to the left or to the right? Trick question. Neither. Normally, you're not, okay, there's a bunch of cases where you could cut like maybe over here, and away from the centroid would be which way?
The right.
The left, right? In this case, it doesn't matter. You can choose either or. It doesn't really, yeah, again, it doesn't really matter here. But we shade in that area. How much is that area? I'm gonna say pi over 8 d squared instead. And then, so yeah, that's basically half the area of a circle. Area of a circle, pi over 4 d squared. Half of that is pi over 8. That's the area that we just shaded in. Now we have to say, what is y bar? Y bar is going to be the distance between two centroids. The first centroid is going to be the centroid of the entire shape, right here. The one that we love. And then the second centroid is going to be the one of the shape that we just shaded in. So this shape is a semicircle. It's going to be like around here. This is our y bar. Does anyone know what that y bar is off the dome? Not a single soul. Somebody fact check on Google for me. Look up centroid of a semicircle. It'll probably be 4r over 3 pi. I'm doing it as 2d over 3 pi because we like d. We like diameters. I don't know what I'm saying anymore. So yeah, this would be your Q, and then that would be it. Okay. I think we'll do another shear thing before we're done here. So if this is confusing to you, that's okay. I think it's less confusing for an IB. But yeah, any questions on the shear stuff before I move on? That's it. It's all symbolic, so it's already all in terms of D's and stuff. You do not have to simplify. At least for the shear part. Good. It'd be fun to simplify. You could simplify. But whatever. Okay, so now what actions do we have? We did both of the V's. What should I do next? MZ. Okay. Is this too cluttered? Should I erase it again like I did last time? Okay. Oh God. Guys, I got like no sleep last night. But it's all my fault. I could have done all this work like over the weekend, but instead I just laid around and did nothing. It was beautiful. But I'm paying for it now. All right, here's our MZ. How do we determine stress due to a moment? My over I. Okay, so I'm going to say sigma bend. We only have one moment, so I'm just going to call it sigma bend, and that's going to be okay. Is equal to my over I. Okay, to replace our thing. So the first thing is going to be mz. What is our y going to be? Radius. Wrong. D over 2. Okay, so what does y mean? Okay, here it's d over 2. In general, what does y mean? In the context of my over I.
This is the centroid.
Not the centroid. Close though. Centroid to what? What were we going to say? What's the other point? The point of interest, right? We're measuring from our moment to the point of interest, right? This is very easily something you may have. If we had an my, what would the stress do to my be? Nothing. Because look, our moment is crossing through the point of interest. And so the distance between our moment and the point of interest is 0. Because remember, our moment is a vector. Vectors have infinite line of action, right? I'm saying if you had an MY, just to clarify what I'm talking about here. And so that would cause zero stress at that point because it's going through. So it's a very important distinction. Because if you said it's from the centroid to the point of interest, it'd still be d over 2, which would be wrong. Okay. I don't think you can reduce that anymore. Is it going to cause tension or compression at our point B? So use our right hand rule. Put our finger right here, thumb in the direction, fingers are doing the action. Is that coming out or going in? Which is tension, so it's positive. You could say like tension. I hear a lot of chatter. Do we have questions? Should I back up?
Just a little bit, understanding the Q value, is it the same Q value for both of the shears because we're working with like a, how does the Q value different?
Okay, so the Q values are different because we made 2 different cuts. For the VY, we made a cut. Okay, so for the VY, our shear flow is going up, and so we had to make a cut that's perpendicular to that, so it's horizontal. When we make a cut here, we say the area that we separated from the rest of it is 0. And so our Q is 0, and therefore our stress is 0. So this Q is 0. Because, so Q is equal to A, Y bar is equal to 0. Because of that. When we made this cut, if we look above the cut, there's no area. There's no area. And so our A is equal to 0, Q is equal to 0, the whole thing is equal to 0. But when you look at the VZ, I think, right? Yeah. When we look at the VZ, our shear flow is going horizontal, and so our cut, therefore, is going to be perpendicular to that. It's going to be vertical. When we make a cut, there's actual area that we just cut. We actually just made a real cut. We didn't make a 0 cut. And so there's going to be area that we have to account for. That area is the pi over 8d squared. The Y bar is what I just found. You should write this down because it's going to be something on the exam that you could possibly lose points for. Did anybody fact check it?
Yes.
Thank you. Off the dome. Only took me 3 semesters. Okay, did that clarify? Okay. You kidding?
Oh my god. You gotta change the screen time.
Yeah. I'm not gonna do that. Okay, any other actions? Am I missing any actions? Yes, Ben, you are missing an action. What's the last action? The torque. So, the torque, how do we solve for shear stress due to a torque? Okay, so we say sigma or tau torsion is equal to TC over J. Okay, so just to clarify, in the problem statement it says I and J can remain as variables. Otherwise, I'd be writing them as, I'm just gonna write this, you probably won't need it, but just in case you need it, on the equation sheet somewhere. It specifically said you can leave them as variables, so that's why I'm leaving them as variables. But yeah, okay, so T is going to be our Tx. What is C going to be? This time it is centroid to point of interest. And so that's going to be d over 2 in this case. And just to clarify, I'm using d a lot because I'm a mechanical engineer, and we're all engineers here. We're not physicists. And so if you put a radius there, I'm sure it won't be the end of the world. But definitely get in the habit of using d instead of r, because nobody wants to spec out the radius of the shaft or a pipe. Or maybe they do actually with pipes, I don't know. Yeah?
Why, so why was this one from the centroid to the point of interest, the last one?
Because we're solving for, it's just the way the 2 equations work. For a moment, technically, our torque is going through the centroid. You can think of it as from the torque to the point of interest. Because remember, our torque is going into the board like, am I going the right way?
So is it the neutral axis to the point of interest?
Nope. It's the moment to the point of interest for bending.
The moment, okay.
And the neutral, so in this case, those 2 things are not the same thing? I'm not sure actually. There's like some more circle trickery you could probably do to find the neutral axis, but I don't know where the neutral axis is. Strange. With shear stress, I don't know how that changes. But the moment and the neutral axis are typically in the same spot, but not always, right? Especially when you have combined loading like this, it's not in the same spot. You're always measuring from, it's going through the centroid, but it's not the centroid. Just because it's going through the centroid doesn't mean it is the centroid.
Okay.
And so it's the MZ, this MZ is a line of action that goes off forever. You're measuring from that point. Or from that vector.
In like every case or moment is gonna be through the centroid.
Yes.
So, okay, so you could basically say that, but technically it's not right?
The only thing that's different is if we had an MY. Because it's the same thing, right? Oh, just measure from the centroid. No, because our MY is going through the point of interest now. And then the distance is 0, so the stress is 0. So that's when it becomes important.
Okay, got it.
Yeah.
What's that equation here? J is equal to 2I.
This is the definition of J. This is the definition of I for a circle. J only has physical meaning in the sense of a circle. So,
It's always 2I.
yes. 2 times the I of a circle, you could say.
So I is the area moment, and then J is the point moment.
Yeah.
What is the exponent on I?
Yeah, d to the what?
4.
Would it be accurate to say the perpendicular distance from the moment?
Yes.
Okay, yeah.
Shortest distance, yeah.
Okay, makes sense.
100%. And yeah, like I was gonna say this before we got a little bit sidetracked, not sidetracked, but like, remember the torque is like actually, the torque is doing like this, right? The arrow is like coming out of us. And so you could think of it actually as the exact same thing. It's just the distance from the torque. Because the torque technically is going through the centroid. It's kind of the same thing as the moment if you think about it for a bit.
So the torque is like, we could also technically draw the torque as like a circle with the dot like coming out from the center.
You can't do it because it's a double arrow. That's not the, I think the notation for that is like,
Okay.
yeah. I didn't draw it again, but here's TX.
But like in theory, if you could find some way to make it a double arrow, that's.
I don't know if there's any notation for that, but yes, that's exactly. It's right-hand rule that allows us to like kind of transform between those two.
We're just writing it like on the top because that's how you can do it visually.
Yes,
Of course.
exactly.
Of course.
Yeah.
So like in the previous problem, it was we were putting our like hand in the direction of force, right,
Mhm.
to figure out the action. And now it's like we're putting our thumb in the direction because we have the action. Now we're trying to see like what the magnitude of that was.
It's kind of different now because we don't know what the action is. We only know which way the thumb is going because we know we have, or sorry, in this one it's different because we know, for the moment, we know where the thumb's going because we have the double arrow.
Mhm.
For the TX, the way that our notation for TX is, we know what the fingers are doing. The fingers are doing this. The thumb is going out this way because we know what the fingers are doing. It's
Okay.
kind of like, I don't know, like any of these problems, it's like you have one equation, one unknown. Like, our unknown is which way the thumb is going, our known is which way the fingers are going. I don't know, that's kind of stupid. But yeah.
Yeah, but in the previous problem, it was only like, you know, put your hand this way and then see where you're.
Because in the previous problem, we're trying to find which way the arrows are going. We don't know where the thumbs are. We're trying to find the thumbs. Okay, any other questions? Okay, last thing here is our VZ. Okay, actually it's fine. I think this is good. So one thing you might be worried about is the VY, or wait, no, we have a VZ. So the VZ is going this way, and at the point of interest, at B, which way is the torque causing shear stress? So the torque is going around, and then which way is it going right here? Positive Z, also to the left, yeah. And so the total torque, or the total shear stress is going to be equal to the sum of these because of that. Does that kind of make sense? This is maybe not a necessary step to do.
This is if VZ is going that way.
Yeah, so if VZ was going the other way, like if it was going that way and they're going opposite directions, you'd subtract.
So in the picture, they are going opposite directions, right? So.
Wow, I didn't see that. I think I was looking at, what was I looking at? I was just looking at the Z-axis maybe?
When we had done it in the like in part A, we determined that VZ was to the left, but this is just like an arbitrary.
So yeah, there's a lot of stuff with shear that's arbitrary. We're about to do more circle, and I'm about to vent to you guys about how arbitrary shear is. At least the sign convention for it. But yeah, I don't even know if technically you should do this step, but this is basically saying like, yeah, the shear is going, the torsion's going to the left there, the shear is going to the right. The shear that you're gonna put in your Moore circle, if you're going from that step to Moore circle, would be the opposite of a sum. Is there a word for that?
Difference?
The difference between them. Okay, any other questions about this part? I don't think you would have to do this. I'm just being a bit of a stickler. And I made the torsion negative because it's going in the, never mind.
Yeah, that's
But yeah, the signs are kind of arbitrary. But I genuinely probably would not even do this step. Don't even worry about that. As long as you get the stresses caused by each of them, I think you're fine. What does it say? Determine the resulting stresses at B, and write out the equations you would have to use to compute the stresses. Yeah, okay, we're good. Okay, good? Cool. I like being over here. I think this is fine. Are there people who would rather me go over there for a bit, or we're all good? Cool. Okay.
Can I take a picture?
Yep. I was gonna ask. Any other people want to take a picture? You can catch it on the video.
How are you posting the video?
I don't know. I'm probably gonna upload it to YouTube or something. I think.
You upload OnlyFans for this or?
OnlyFans. Bro, was that off the dome? That was good, man. Can I erase? I'm erasing. Holy. I've already got some other stuff on there that I don't want y'all to see. Hendrix already knows, bro. I'm bringing you into this.
You're editing this out, right?
No, I'm not editing shit. Why are you not propping it up anymore?
You couldn't see it.
Oh, really? Thank you so much for doing this.
Yeah, of course.
First he tells me to stop answering.
Good night. I think we're gonna get all the Moore circle out in the next 20 minutes. I don't wanna like come back and do more Moore circle. So
there's going to be no 3D Moore circle, it's only going to be like that.
I would eat my own Shigleys if I would eat my Shigleys and ask for seconds if you guys have a 3D Moore circle on anything.
I'm gonna look into that.
Okay. What did he say? He said there's none?
He said there's not gonna be any.
Okay.
Oh, okay.
In that case, you can riot if he does. Okay, lock it in. We only got an hour left. Only one more hour. Okay, so how do we do Moore circle? What am I doing? What's the point of Moore circle? So just because we set up a coordinate system that's in this XZ orientation, it doesn't mean that our maximum stresses are going to be the same there. If we set up a coordinate system that is angled or like spun around, you're going to get different numbers. And so the maximum value of our stresses are not necessarily going to be in the X and Y orientation. In this case, they will be, yeah.
Can you like, I think you did on another exam, like can you replace like the Z-axis with like, we call it X, and then replace the X-axis and call it Y?
If you wrote that out on the exam, I don't see any reason why you couldn't. Like I said earlier, like symbols and coordinate systems and everything, they're all just like labels we use to communicate this information to each other. And so if you're very clear about what you're doing, you can change it however you like. Okay, I kind of want to add a shear to this because this is way too easy. I'm going to add a shear to it. So that you guys know what to do. How many, a full year of doing statics and like strengths and materials, and you say Moore circle is the only thing you can do? For God's sake. What you make the towel?
Then we get a good number, 4.
I like 4. Better than 27. That's a good number. That's a good number right there. Okay, so what do I do now? Plot it on what? What would I plot it on? Make a graph. Here's x. Okay, so we have a sigma. Sigma axis is our horizontal axis. Our tau axis is our vertical axis. What the hell? I was going to say a bad word. What the hell is positive and negative shear stress mean? What does that mean? What the hell? So who here is a mech or mecha? Who here isn't? Okay, so half of you guys about are going to go to 340 next semester with our GOAT doc. And he's going to teach you a way of this that's way cooler. And that's, you don't have to do this. You probably shouldn't do it because it would just confuse Hazelton. I'll just tell you that. I won't write it. I don't want you guys writing it down and like being like, oh, I did this in my notes. And then you do it on the exam and then Hazelton gets confused and it's a whole mess. But basically, do you see how the 3 megapascals has these 2 arrows kind of it's going into these 2 arrows? The left and right one? Which way are those 2 arrows going? About like counterclockwise. They're going counterclockwise, right? What about these 2 arrows of the 6 megapascals? Which way are they going? They're going different directions, right? One of them's clockwise, one of them's counterclockwise. And so the way that you determine which one is going to be the positive and which one's the negative is based off that. And so, yeah, the direction or the sign is kind of arbitrary. So I'm just going to make it arbitrary. Based on this one is clockwise, so I'm going to make it negative. So yeah, next step is you plot 2 points. So what 2 points do you plot? You plot kind of like the stress state of your x, what is it called here? Your z and your x coordinates. So I'm going to start off by doing the x, which is vertical in this case. So what is the x coordinate, or sorry, the sigma coordinate of this guy going to be? Why is it negative? Compression. So we have -6 right here. What is the y coordinate or the tau coordinate going to be? So I decided arbitrarily that since it's going clockwise, I'm going to make that negative. So we're going to make it a negative. But what is the value of that going to be? -4. -4, thank you. Okay, so here is the point now that we plot. Perfect. Okay, where is the other point going to be? 3, because it's in tension. And then it's going to be +4. It's just on the opposite side. It's mirrored, basically, about the x-axis. And so now I draw a line between them. And then I draw my big circle. Who's excited? Come on. Come on. I know you're excited. Good. Oh. Oh, that's ass. That's ass. Never mind. I was going to say something that should not be recorded. Okay, so now, what now? Find the radius. We could do that. Find the center. How am I going to find the center? Average of our 2 points. So if we look at our y-average, we can see that we have +4 and -4. The average between those is just always going to be 0, right? And that kind of makes sense. Look at where I drew it. Your center is always going to lie on the sigma or the x-axis. How about our x-average? How do we do that? So we have a +3 and a -6. What is the average between those? Add them up. So 3 plus -6 is equal to, divided by the number of things we're averaging, which is 2 things we're averaging. -1.5 is what we get. So -1.5. I'm going to write all the equations down later if you get confused here. But yeah, we just found the midpoint between these two, and that's -1.5. So we can say C is equal to -1.5. Now what do? Someone said it earlier, they jumped the gun, but now it's their time to shine. Radius time. So now we can look at this guy. This is like a triangle right here. You can look at the other one too. It doesn't matter. It's either one. Yeah.
How do you decide like which one corresponds to positive, one which corresponds to negative?
I made it the hell up.
So you must have like another one that's like
It's going to give you the exact same. I'll show you the equations for everything later. The only thing that changes is whether you're looking at it like this or like this.
Yeah, so if it's the same.
It doesn't change any of the numbers. Yeah. That answer your question? Okay. I've told people a billion times to like ask Dr. Hazelton if he cares or not, and not a single soul has gone back to me. And nobody, I know none of you here have an answer for me on that either. So if you feel like trying to make that happen, you can't, because you have 2 days until the exam, and you won't see Hazelton until the exam. Does he have an office hours report?
He might not even be there for the exam if he's sick.
If he's still
still.
sick, yeah. I don't know what to tell you. Flip a coin,
Email him.
you'll be fine. You can, yeah, good luck, email him, yeah.
Yeah, that'll work.
Okay, back to our thing of interest here. We know our center's right here, and all the way out to the edge of the circle is right here. What do we call that distance from center to the outer part of a circle? Radius, that's what we're looking for. In this case, we do care about the radius, not the diameter, for once. So we can make a little triangle here, right? We have a right triangle. How can we find this hypotenuse? What is an important equation for finding those?
A squared plus B squared.
You're a genius. Who said that?
I did.
Extra credit.
Yay.
No. Minus credit.
It's because I went to your,
The drop-in. Hey guys, I have drop-ins for next week and this week and then next week. And both of them are after your exam. So, yeah. Maybe you should write that down. So.
Do I get extra credit for advertising your drop-in hours?
Yeah, in my heart, you get extra credit.
Yeah.
Yeah? It's too late for that. No, I'm just kidding. If somebody wants to sign up, they can ask me.
11?
Huh?
Oh, my brother doesn't sense.
You can just pull up, man. I don't know about Friday. You have to. I have certain people who I won't name who sign up like every like blue moon for Friday. Like right before the exam. It's kind of weird. So you could sign up for the Friday one as well, I think. Just to make sure if those people cancel on me. Okay, back to the problem. So we were interested in finding this hypotenuse. So now we have to look at our two sides here. Which side do we know? Which side's easy? 4. Do you see how if we looked at this side, it wouldn't matter that this was negative because we're just finding like distances? It's gonna be a 4. So we're gonna say square root of 4 squared plus, huh? Okay, plus, what's this side gonna be? How do we find this side? It's 4.5. You can see it, you just look at it and you're like, okay, 3 plus 1.5 gives us 4.5. Okay, and then somebody with a calculator surely will get this for me. 6.02. Thank you guys. Okay, cool. Now we have our C, we have our R. How do we proceed? What do we do?
C plus R will get your max.
How do we define the max? What's the definition of our maximum stress, maximum normal stress? 1 on the right. Can we be more rigorous about that? So the further we go to the right, what's happening to our normal stress? It's becoming more tensile. It's our highest tensile stress. And that could still be negative, but it's still the highest, it's the closest to tension that we've got. If our Mohr circle was like over here, for instance. How about our sigma min? How is that defined? It's the most compressed stress that we have. And so either of these can have the highest absolute value. In this case, the min is actually going to have a higher absolute value than the max, right? Because, or wait, what?
Yeah.
Did I do that right?
You don't have to.
Yeah. Okay, cool. Doing it all in my head. But yeah, so in this case, our min technically has a higher absolute value because this is 4.52, this is 7.52, but this one's negative. It's more compressive, so we call it our minimum. Okay? How do we find our maximum tau? It's just equal to the radius. So tau max equals radius. And in this case, we don't care about the, and these are all in megapascals. You should write your units. I'll write my units. In this case, we don't care about what min means because, like I said earlier, the most negative one is actually the same as the most positive one. And also, we don't care, like, shear stress doesn't matter whether it's positive or negative. There's no physical meaning to that. Whereas normal stress, compressive versus tensile, that does matter. That's important for reasons. Does anyone know what these are? Materials. Some materials perform differently under tension versus compression. All materials perform differently, actually, in fact. But some of them are like weaker in one state or the other. So, okay. I'm going to give you the equations for everything here so that you can just do it whenever. I'm going to call them sigma x and sigma y. I don't think it actually, sigma x is just going to be the horizontal one, sigma y is going to be the vertical one. So we called it x and z here. X is just going to be horizontal, y is going to be vertical. So your c is going to be, what am I doing? Sigma x plus sigma y over 2. I don't know why I did parentheses. R is going to be square root of okay, and then what if we were asked to find the angle? Does anyone know what the angle is to get to the maximum, the principal stresses from here? Because this, what my arm is doing, that's kind of like our like Cartesian stress state. How do we get to our principal stress state? Which way do I rotate? Clockwise, right? Do you see how like I move my arm this way? It's clockwise from here. So we're going clockwise. That would mean the coordinate system that we'd have to measure in is this way. I don't think we really need that anymore. And so this angle right here is what you would get. And so you say tangent, and it's 2 theta. Who here knew about the 2 theta thing? Some people were telling me that, wow.
I only knew about it because you told me.
Nobody knows about the 2 theta thing.
What do you mean then?
So every degree that you move in Mohr's circle is 2 degrees in the real world. Did we know about that?
Yeah.
Okay, nobody raised their hands. So the only thing is you just write 2 theta here instead of when you solve, you just get, yeah. Okay, so that's going to be 4 over 4.5. You can do algebra. Okay, cool. I think we're done with Mohr's circle. Yeah. No, there's going to be no 3D Mohr's circle. What we just did is going to be on the midterm. Just what we did right now.
Dos B. Dos B. Dos B. 2D. B.
What kind of question where when tangent
Dude, all my classes say it would say like find the
It's
angle
like every
to
teacher
the
taking your research sabbatical
the
this
principal
semester.
stress state or whatever.
Because I guess your song is like super into for
Principal stresses are sigma max. And so in order to get from
I'm not taking it. Theta x minus theta y divided by tau.
I don't know that off the top of my head. I think that sounds that sounds right. Because like this is it would be this. It'd be that over that.
Oh, but you're gonna switch to
So it'd be 2 tau xy over sigma x minus sigma y.
Yeah.
Okay.
Don't let it in. You tell them
Raise your
what
hand.
Should I switch this over to read that out? What do you think? I'll get job
I have no idea.
Would you hire him?
I might.
Diversity.
I need a job so bad. Hendrix, please give me a job. Please hire me.
No, that's my job. I can't give you my job.
You can have it, you fired your.
Please, I'll be your assistant. Can I do anything?
Have you worked for NASA?
He literally works at NASA, bro.
If you haven't had an official position.
I don't want to do this.
You should just hire all of us.
Is this with the table method?
Yeah.
Expand north south.
This is table method.
Do you know if we're just doing table method?
We'll go farther north.
No one's taking order.
Do you know if the second
Wow.
is final?
You said there might be a question where we have to like set up the
The boundary conditions.
We'll
talk about it.
I don't know how to do that though, but.
That's actually why.
I'm getting some water real quick. We'll take a quick
Just don't
break.
file the taxes, I'll tell you.
Never heard of it.
On Thursday.
Look, we can zoom stuff.
Next what? Oh, next NASA?
Yeah, all these kids are NASA too.
We're gonna go back?
We're gonna fly backwards.
Go to Mars?
We're gonna get a building.
Can we go to Mercury? Why does no one want to go to Mercury?
That's a planet.
Well, everyone wants to go to Mars. You're still gonna die on Mars.
You're less likely.
Slightly
No,
less.
they're gonna terraform it.
We can terraform Mercury too, guys. It's actually kind of like, it's gonna be easier to go to Mercury than Mars, right?
I believe so. I feel like the environment by now if I were
is a lot.
It's literally just the distance though. And you have the sun as a gravity well that's helping you.
I think
So like, that's gonna be way less.
Yeah, but I think Mercury's way hotter.
Yeah, but like, who cares?
heat transfer.
Your body.
Heat transfer. Did you say
The spacecraft you take there.
That was what I said earlier.
There's a couple of variables.
Isn't it easier to fix Earth than terraform Mars?
5%. What the hell?
What's terraform?
Transform is out of our paycheck.
It's out of our scope.
You'll learn that in the next
Making
class.
something habitable.
Dude, can I outline your diagram? That's so good.
Rudy can stop himself.
It's autopilot. It's a default setting. Right, Ben? I'm making too many bad jokes. And I just wanted to, what's a default setting?
That one was genuinely like bad.
Which one?
I might edit it, guys. We might have to edit it. What was he saying over there?
I've just been talking about more circles.
That's bad.
What was Moore doing?
Oh, I'm sure
He
you
was
can't
moving,
find out.
he was moving like. He was going like. That's gonna be the best joke I've ever made. Alright, 2-minute break over. Have a good night. Oh shit, dude, I was supposed to bring a fucking. I even had the sign-in sheet. The sign-in sheet. Fuck. I'm gonna make one. Just a piece of paper. I need to go run after that guy.
That's money that we should bet.
You're betting up, eh?
Yeah, thank you. That's money that could be in my pocket.
Put a fake name.
Wait, do you get paid for students?
No, I've said this a million times.
Put George's name on there again.
I'll get her SDSU ID real quick.
It's just student ID and like, what else?
And the date and the time.
Date and time. And social.
And last 4 digits of your
Bank account number.
Social security, your bank account number. The name of your pet.
Your mom's maiden name.
Is it 27?
Yes.
The sign-in, we're gonna run out of space on that.
Nah, there's 2 sides.
I know, but I'm gonna feel like, whatever. Okay, shit.
His little eye roll.
I don't wanna do this. I hate this process. Alright, I'm gonna get started again. Can we get order? Okay. This is a deflection problem. How long did you guys go over deflection for? Who said it twice? Who's skipping Katie? Alright, that's getting edited out. We're editing that out.
I should have planned it.
Yeah, I'm very surprised that it's on the exam. I did not expect it to be in the exam. So
It's no moving area though.
that's how it normally is. He's acting like that's some big concession he's giving you guys. So like that's like normal. Okay, so there's two main sorts of problems. You have just finding deflection at a certain point, and then you have deformation compatibility. And so this deformation compatibility is exactly the same as the stuff you did in midterm 1. That's going to come back to haunt you in a week when you study for the final. It's just different because you're using it in the bending context. Does anyone know the governing equation for bending? Nope. Bending, deformation, bending, deflection.
Oh, the heel over
Nope. That's axial deformation.
the
I heard EI.
yeah.
Negative PL squared.
What?
That's wrong one.
This is the governing equation of deflection. And so if you guys were asked to do the integration of this, that would mean you'd have to take two integrals to get your y. The idea being that E and I are generally constant. What is E? And what is it a property of? Material. So if we have the same material throughout, that's going to be constant. We're integrating with respect to x. That's going to be constant, so you can pull it out of the integral. What about I? What is I based off of? What is that? It's shape. It's based off your shape. It's your second moment of area. Wait. And so if your shape is, your cross section is constant throughout the whole thing, you can pull that out of the integral as well. And the only thing you're left with is m. M is a function of x. How do you find m as a function of x? How do you find like something that shows you the moment at every point on the beam?
Oh, the crack.
What do we call it? So it's called a moment diagram. Diagram that shows you your moments. So using your shear moment diagram, you can get m as a function of x, and with that you can get like this m right here. And so you take integrals. I guess I should just get to it. I don't want to really do it, but I have to. Okay, so the lucky thing about this is we don't have to take all these integrals because people have already done them for us. And so the idea behind this problem is we can, instead of looking at it as a beam that has a fixed support and a roller and these two weird loads, we can look at it as just a cantilever. What does cantilever mean? Fixed on one end, free on the other. And we can say that we have a bunch of loads on it. And so the first load would be this guy. Second load would be this guy. And then what's the third load going to be? The reaction, right? Which way is the reaction going? Up. Can it go down?
Negatively.
Okay, so it's a roller. All the roller does is it's just the ground pushing against you. The ground can never suck you down into it, right? The ground's never gonna. What about quicksand? I hear you say. The ground can only push against you. And so that means that we can treat our reaction as like a point load like this. And so superposition principle says, oh my god, if I got that, I would say.
Edit that.
Superposition principle says that we can look at each of these competing effects, calculate the deformations of each of them individually, and add them all up again to get the total deformation. And so what that means is we have to say the deformation of this guy, this is equal to the deformation of this guy plus the deformation of this guy. And we have to do something special with this guy. was the deformation of this guy.
How did your beam like get more curved as you like, it's kind of like, it's like almost a C.
Because it's already deflecting.
Keep asking questions. See what happens.
I'll learn.
True. Okay, can someone tell me what's wrong with this one?
Not in the table.
Not in the table. So let's look at the table. I was talking about the table earlier. Basically, somebody took all the integrals already. You don't have to take any more. Why am I in the shapes, right? For design project. Okay, so when you're looking at the table, you see there are 7 different loading conditions. Which ones do we might we possibly care about? The first thing to delineate is to say what is my
Cantilever.
what is my structure? Is it simply supported or cantilever? And so, thank you for letting me use the accent. So if we look at the top 3 right here, these are the only ones that are cantilevered. Of them, we have a point load at the end, distributed load across the whole thing, and then a point moment at the end. Which of these do we care about? The first two. So the first one right here is the best one because that's basically what we have for case, we'll call it case 3. I'm going to call it case 2.
Nah, that's something. Let's draw it.
I'm not going to call it case anything yet. How about for the first case I've drawn in there where the distributed load's going up at the beginning? What's up with that? How do we do that in with these? I don't see that on here.
You just do it for like how many distributed loads.
Huh?
Multiply a negative into it.
Multiply a negative into it?
So the maximum deflection.
Oh, I didn't mean that. But yeah. In this case, the distributed load is going across the whole thing. In this one, it only goes about like halfway down or whatever. And so we'll get to it later. But basically what happens is it curves like this, following the rules of that. And then once it hits the end of the distributed load, what happens? It goes in a straight line. Why does it go in a straight line? I'm glad you asked. Because when we hit the end of the distributed load, what happens to our moment? Our internal moment hits what? 0. If you were to draw a shear moment diagram of that loading condition, sorry, the one where you have the extra beam hanging off, you would see that the moment once you hit the end of the distributed load hits 0. And it just keeps going off at 0. And so if we look at here, if d square y dx square is equal to 0, that means that, what is the left-hand side? The left-hand side is the rate of change of the rate of change of your position. The rate of change of your position is your slope. And so it's saying this is the rate of change of your slope. And so if the rate of change of your slope is 0, that means your slope isn't changing. If you have an unchanging slope, what can we say? Straight line. I just wanted to tell you guys about that. Apologies. I like it when you guys understand things. So, okay. So that means this is going to look something like this, right? We can calculate that. How about this guy? This guy's the problem child. How do we do this?
Put a distributed load across the whole thing, and then put another distributed load going up for the first half.
For sure. For sure. We're gonna do this. Really?
Yeah.
Dude, you're gonna lose your tongue tonight, by the way. I'm killing you soon. Do they have the same W?
Yeah. Well, one's a negative. It's negative deflection, one's positive. Okay. The first one, if you made it an entire one, would be positive.
that's on top. What is it? It's the same thing.
And since we already calculated that, we should times the other one by 2.
I thought you said like K and something else.
No, I did.
You did? Yeah.
Okay, so
was asking why it was on top. And,
pretty important thing here that I just did. Basically, the guy we had before, where it's this guy going down, we don't see that in our book. And so the way that we account for it is by saying, we're gonna do the whole thing. So this guy's saying only at the end go down. This guy right here is saying at the whole thing go down, but then also add this guy that's going up at the beginning to counteract that. And so we can see that this guy going up at the beginning is the same as this guy. Wait, is this the same?
Yeah.
This is the same as that guy, so whatever we calculate here, we can just multiply by 2 and not have to think about this. Does that make sense to everybody?
Yes.
Okay, cool. Now I think it's time to do some numbers. Okay, so starting off with, I'm gonna call them 1, 2, and 3. I'm gonna start off with 3 because it's the easiest. I'm also gonna talk a little bit about, my God, what are the, I didn't even label points. A, C, B, are you kidding? A, C, and B, mother of God. Okay, L over 2. L over 2. And then there's a bunch of numbers. I don't care about the numbers. Okay, so for in terms of how we label things, we're gonna say they're all deltas, right? All the deformations are gonna be deltas. They need to all have a subscript. This is especially important if you guys get the one that says solve symbolically, right? Because the only thing that you can screw up there is your subscripts. There's nothing else you can screw up, right? And so we're gonna be very, how do you say? We're gonna be very precise when it comes to our subscripts. If you have one letter here, this means it's the absolute deformation from the undeformed bar of A. In this case, what is delta A gonna be? 0, because it's fixed to the wall. If you say something like delta B with respect to A, this slash means B with respect to A. That means that with respect to where that point is, how far did B deform? And so this is a bad example. We'll get to the example in a sec. But yeah, so that's how it is for your point. And then you add a comma when you're doing these like cases, these 3 cases that we're looking at. You add a comma to say like, oh, we're looking at case 2 or case 3 or whatever. So I'm clarifying this now before we get into it. It's gonna make more sense when I actually do it. Okay. Or you already understand it. That would be best. Okay, so 3 is the easiest one. So we're gonna look, what we're interested in is the deformation at point B. I never even talked about it. Why are we interested in the deformation at point B?
It's our max deformation.
Is it deforming? So in the original thing, imagine if the roller was not there. Do you think that would be deformed down or up? Why down?
The force is acting farther.
Yes, there's more of a lever arm. So imagine that the roller isn't there. We have 2 equivalent distributed loads, one acting up and one acting down. The only difference between them being that one of them is further away from the fixed support and one of them is closer to the fixed support. Meaning, one of them is going to cause less of a moment because it's closer. And so the one that's further away is the one going down, and so therefore that one's going to win. The whole thing's going to want to deform down. However, we have a support there. And so that's how we know that this RY is going to exist, is because we know that it was going to go down before. The support being there means that it's going to want to bring it back up to 0. And so I just said it there, but what is the total deformation of B going to be? 0, because we have a support there. Okay. So this is like our deformation compatibility is saying delta B is equal to 0. And then you can say delta B is equal to delta B1 plus delta B2 plus delta B3. This will be very important if you're doing the symbolic thing. If you're doing the symbolic thing, this is all very important. Now we have to say, how do we find delta B1, delta B2, and delta B3? It's by using our equation. So delta B3 is equal to, we just look at our thing. So we say, first of all, is it going up or down?
Going up.
For case 3. I'm starting with 3. Sorry about that. It's the easiest one.
Going up.
It's going up. So we're going to keep it positive. Our P is going to be what? Our Y. What is our L going to be? Because this whole thing is L, and in there, L is the whole thing. We're just going to keep it L. And that's L cubed, right?
Yeah.
Yeah, and then over 3EI, that part isn't very special. Okay, I could calculate the coefficient if we wanted to, but it's still gonna have the RY there. We don't know what RY is. That's what we're trying to find. Okay, now we can do you want to do delta B1 or delta B2? I think B2 is easier. We'll do B2. So delta B2 is going to be equal to what? So we look at our thing. The entire thing is a distributed load and it's going down. That's exactly what we have right there. We don't really have to change that much. So we're going to have negative W. What is L going to be? Trick question. It's still going to be L because this L right here is this whole L. So we have L to the fourth, right? Over 80i? Yeah. Okay. All right, so here's the hard part, quote unquote. I'm going to draw it again over here. So we're going to have okay, so like I said earlier, it's going to be curvy at the beginning. And then once it hits this little spot right here, this is C. Once it's C, it's going to go in a straight line up until the end. I heard of what? Okay. This is case 1. Yeah, we're doing case 1. Case 2 and 3 were pretty simple because it's literally the exact same thing on the diagram. Okay, so starting from here, what can we find? What can we find? What can we find? What can we find? Displacement and angle at C is what we're going to need. So starting off, we could say displacement of C in case 1 is going to be equal to positive or negative? Positive or negative? Thank you. It's going to be W. What is our L going to be? L over 2 this time, because we're only going halfway down the beam. To the fourth power?
Yeah.
And it's going to be still over 80i. And then now we have delta, no, we have theta. Theta C1 is equal to what?
Negative W over WL cubed.
So it's going to be negative?
Positive.
Positive. WL
Cubed.
cubed. What is our L?
L over 2.
Over 60i?
Yeah.
Okay. Now, what do we do with those things? We're interested in this. This whole thing here is delta B1. This is what we want. We just got this. Does anyone see a right triangle here anywhere?
No.
Okay. Right, so like we said earlier, this is a straight line. And so we can create a little horizontal right here, a little vertical right here. We got a right triangle. You can think of it as a right triangle, or you can think of it just in terms of like rise over run. What we calculated right here, again, these are all numbers we know. W, L, E, and I are all given. We can put that in our calculator, lickety split. But I'm not going to do that because, in the interest of time, we have 10 minutes or something. My God, I'm not going I'll probably go all the way to 7. What we have here, this is a slope, but by small angle approximation, it's also kind of like an angle as well. If you're not familiar with small angle approximation, it basically means for very small angles, like that of a beam bending, like if you stand on a steel beam, it's not going to bend that far, really. The sine of that angle is basically equivalent to that angle. Cosine of that angle is basically equivalent to 1. And then tangent of that angle by proxy is equivalent to theta. And so you can think of it either as rise over run or as an angle thing. It's whatever floats your boat, really. And so, yes, if we know this angle, I'll treat it as an angle at first. We can say this is delta or theta C1. We are looking for this guy right here, which is, what is this? Distance right here.
Delta C with respect to B.
Delta C with respect to B, 1. This is saying right here, it's saying from C, how far do I got to go to get to B? That's what this is saying.
Wouldn't it be deflection? B with respect to C?
Yes, correct. My bad. I was testing you. And you passed. Yeah.
Because they put C in the middle.
Yeah, I'm just pissed about how the fact that they put C in the middle, but yeah. You're right. Okay, and so now we can say like delta B1 is equal to delta B C1 plus delta. My God.
Are we allowed to put like C minus B, like delta C minus B?
What do you mean?
For instead of B with respect to C?
This is the. So I mean, I've talked about notation a little bit today. As long as you're clear about what you're saying, it should be fine.
Okay.
But also, it's nice to use the same notation that everyone else is using, so that we're all on the same page.
Make it easy, yeah.
And so this is the notation that we were born into. And so we could use it. So okay, and so now yeah, how do we find delta B with respect to C? We use either trig or rise over run. And so we can say our slope is equal to rise over run. How far are we rising? Delta B with respect to C1 is how far we're rising from here. And then how far are we running? L over 2. Does this make sense to everybody? We have a slope right here. Going from here to here, we rose by delta B with respect to C1. And then we ran for L over 2. I don't have the L over 2's labeled, but hopefully you got that down. And then the other way to think about it is, this is a right triangle. We could say tangent of theta C1 is equal to, opposite is delta BC, B with respect to C1. Adjacent is L over 2. And then you can say small angle approximation. Or you can just put in your calculator and it's the same thing because small angle approximation is real. And then, what are we solving for here? Delta, right? So we can say delta B with respect to C1 is equal to L over 2 times theta C1. And so yeah, how many equations do I have? About 1 billion. But how many unknowns do I have now? 0. Wrong. 1. Okay, so from the top, we have our governing thing is delta B is 0, right? We know that because of this reaction, B is not going to sink into the ground, and it's not going to go up either for the reasons of the down one being stronger than the up one that we talked about earlier. And so delta B has to be 0. And we know that delta B is going to be equal to the sum of all these cases. Forgot about this part. Earlier I had this guy and I put him onto this. I have to multiply this guy by 2. Do we all remember that? If that confuses you, raise a hand. Okay. Delta B1 we got as being equal to this thing times 2. Delta B with respect to C1 is equal to L over 2 times theta C1. Theta C1 we got from right here. Delta C1 we got from right here. So that's delta B1. Delta B2 we got from this. Delta B3 we got from that. So we have everything, all of those as being equal to 0. Delta B1 and B2 are all numbers that we can find. Delta B3 is not a number. What is the unknown in this? Ry. That's what we're looking for. And so that's the only unknown. We can do algebra and find it. The only thing that you can really screw up super bad there is just like calculator stuff, because there's a lot of numbers you're putting into places. So be wary of units and try your best. What's up?
So instead of worrying about like small angle approximation or anything like that, can you literally just take the slope and multiply it by L over 2?
Yep. Yeah, that's what I was doing with this one. It's like, this is like slope, and then this is like, you're thinking of it as like a right triangle.
Yeah.
But it gives you the same number. Yep. And the angles are truly so small that like, even if you did the tangent of that, it's still going to do the same thing.
Okay.
But yeah, just think of it as a slope. I think that's easier for most people. So. Okay. I think I will do a shear problem and then we'll be done. Obviously you're an adult, you can leave whenever you want. As long as you sign the sign sheet. Okay. for units to cancel. I'm erasing.
Yeah, this is not nice. This is like questions square. He's in a student. Yeah, lost.
Good night. Stay back. I thought he came back. That would have been awesome. All right. I don't think I have time for fun and games. So let's get into it. The I-beam is subjected to the loading shown. Determine the following at cross-section AA. Internal shear force in cross-section. I don't like this. We're going to do it kind of different. Vertical shear stress at point A. Label stress with proper subscripts. Okay, that's good enough for me. Okay, how do we find shear force at a certain point in a cross-section? Or sorry, on a beam.
Bye, Benjamin.
Bye. Thanks for coming back. I appreciate that.
He still looks like that.
Huh?
He still looks like that.
He said bye, Benjamin. That's good enough for me. If anyone else says bye, Benjamin, though, like, I'm failing you. I'm going to find a way. We'll never say that bye. How do we find internal shear force at a certain point along a beam?
Would it be shear moment diagram?
Shear diagram only. We don't have to do the moment. Yeah. So our reactions are not given. Yes, they are. They're 7.5. So starting from the left-hand side, we have a vertical reaction going up by 7.5, and then we go across by 4 feet, and then we go down by 5, which brings us down to 2.5. I guess this could be 4 feet. And then we go 3 feet. And then we go down by another 5 feet. That brings us to negative 2.5. And then we go across 3 more feet. Wouldn't you believe it? Go down by another 5. And then you go across to the end. You jump back up by the reaction at the end, which is 7.5, brings us to 0. If we didn't get to 0, that would mean that would mean we did something wrong. Okay. Any questions about shear diagram? Hopefully we're all good with this. If not, attend the drop-ins. Why are you making faces at me?
I didn't do anything.
What do you mean you didn't do anything?
Didn't do anything.
You're like the guys who killed Caesar, like it wasn't me. It was all of us.
It wasn't.
Stop. You're scaring me. Okay. Okay, so for this question, it's asking, what is the internal shear force at section A? So how do we find that? We could have done that. That actually would have been faster. In this instance, if it's only asking for the internal shear force at one point, you can just cut it, and that's actually faster than doing the shear diagram. So yeah, if it's asking you for the maximum though, you have to do the shear diagram to see where the maximum is though. But yeah, so in this case, you could have cut it, and you would have come to get, what's our number here? 2.5. So 2.5. V equals 2.5. I don't really care if it's up or down, to be honest with you guys. I don't care about finding that out, and I'm not gonna, you can think about it on your own. Exercise to the reader. Okay, vertical shear stress at point A. So I'm gonna draw my cross section. I'm not gonna draw the dimensions, you guys already have that. Here's point A. Okay, let's say shear is going up. Okay, now there's this idea of shear flow. How is the shear gonna flow through this? Imagine it's like a river and there's water flowing through. That was beautiful. Can you do that again? So it's gonna kind of flow like this. And then when it hits here, it goes over here. Okay. So what's our equation for shear stress due to a shear force?
Tau equals VQ over IT.
Thank you, bro. Okay, so we know our V. Do we know our I? it given?
Yeah.
Where? 494.8? Okay, so how do we find our Q and our T? What's that about again?
Q would be the area, or the area above the top flange, and the Y bar would be like distance from A to central.
Let's do our cut first. So at the point A, which way is the shear flow going? Yeah, it's going like up, like this. So perpendicular to that would be what? Horizontal. So we make a horizontal cut at point A, and then we say our V is 2.5 kips, our I is 494.8 inches to the fourth. What is T going to be? What's T? Thickness of the cut we just made. How thick is our cut? 2 inches, because that's the thickness of the web. They call it a web because it connects the two flanges. All right, so Q is equal to A Y bar. What A are we worried about? Why is it the top and not the bottom? We cut it into 2 shapes.
Centroid.
I don't even see which one of you guys said that. Okay, so here's our centroid. Our cut is right here. We cut it into 2 shapes. We care about the area that's away from the centroid. Away from the centroid in this case is above. So we shade that in. What's the area of that? 9. Because this is 6 inches wide and 1.5 inches tall. So area is going to be equal to 9 inches squared. What about Y bar? What is Y bar? Centroid. Area.
Centroid of that.
Okay, so we need to find the distance of the centroid. So this is like our shape of interest right now, right? The centroid of it's like smack dab in the middle right there. We need to find the distance from that centroid to the center of the whole shape. And so if we look at this whole thing is 8 inches tall. Half of that is going to carry to the centroid. So this is 4 inches. Half of this is going to be 1.5. And so that gives us 4 plus, wait, what? Half of 1.5 gives us 0.75. So 0.75 plus 4 gives us 4.75. Okay, from the top. Half of this, so this centroid is what we care about. This is 0.75, right?
Yeah.
Okay. From here to this, to the edge of the flange is 4 inches because the whole thing is 8 inches tall. Good? And so our Y bar is going to be 4.75 inches. Calculator man, and or woman, and or other. Thank you. Units? Perfect. Dude, whoever that was, I got no words. Okay, what's our shear stress? It's gonna be like 4. Look at this, look at our eye, it's like 400. It's a good thing. That's fantastic. Calculator?
Computer.
0.125?
Yeah.
That's crazy. What are the units? It's a stress. KSI, there you go. Okay. And so that's like nothing, by the way. Like, you feel that in your like pinky toe right now, probably. Okay, so that's the answer to part B. Part C asks us, oh wow, the horizontal in-plane shear stress. Okay, cool. So at point C is over, it's kind of above the web right here. So same process. Where is the shear flow going at point C? It's going like horizontally, and so perpendicular that's going to be vertical. So we make a vertical cut at C, and then we only shade in the region away from the centroid, which is, in this case, to the right, like here. Does that make sense? Okay, and so how thick is our cut?
1.5.
What? 1.5? I thought somebody said 4.5. I would have gotten really angry if that was the case. Okay, now, what is our area? So this whole thing is 6 inches. The web is 2 inches. Not quite. This is right above the web.
1.5 times 2.
Oh. 3 inches squared, because this guy right here is 2. This guy is 1.5 tall. 2 times 1.5 is 3. Have a good minute. Good luck. 3 inches squared. What is our y bar going to be? 1. Part of me thinks it might be like this, but I don't think it is. Check the solution. I don't care. I'm pretty sure it's the 4.75 because that's the axis. We take this axis for our second moment, or for a moment of inertia. So I'm pretty sure it's just about this axis. So I think it's 4.75. You can check the solutions if you think I'm wrong, because we have like 2 minutes left.
That's 7.5 kips, right?
2.5 kips. Because it asks us for the thing of A, we found A to be 2.5. Okay. 3 times 4.75, I'll do it in my head, is 12, plus 2.25 is 14.25. Okay, 14.25. So this is a number. Not quite, because this is 1.5 now.
Oh.
Yep. Zero 48. Okay. That is your answer. Yeah.
How do you know which direction is your logo? It is.
Think of it as like a river and you poured water. Like, it's like a hollow like thing and you poured water into. Which way is the water gonna go?
We should assume it's like perfectly parallel with.
Yeah. I mean, it's not gonna like.
Does it have to be like something that's pushing down on the bottom, stretching more?
The shear stuff is all like black magic. I've seen the derivations for the bending stuff and it makes sense. But this shear stuff is like. Make sure you sign the sheet. My voice hurts so bad.